Welcome to the second lecture, online lecture about holomorphic functions. So we are still in chapter 1, and I will finish it today. I included in the lecture 3 exercises that I hope you will solve before next time. So next time I will provide a solution of the exercises. Okay. Okay, first recall the following. The theorem about differentiation term by term. If you have a power series of a complex variable, of course, you know that it has a radius of convergence, possibly infinite. But I assume here in this that the R is strictly positive. I didn't say that, but I have to assume that R is positive here. Then the series obtained by differentiation term by term has the same radius of convergence, kr. This is the first thing. So we can differentiate term by term a convergent power series, if you like. Now, if the series is divergent, we cannot differentiate term by term usually, in the usual sense. Okay. And now, if we let S of Z be the sum of this convergent series, then this function S is holomorphic on the disk. So this is the notation of a disk. BAR is just the disk of center A and radius R. Okay, it's the usual disk in the complex plane. And so the sum of the series is holomorphic, and its derivative is given by the series obtained by differentiation term by term. Okay, and it follows actually if you repeat this process. So S prime now is the sum of the convergent series. So we can differentiate term by term another time, and you get S double prime, and so on. So if you can, so it means that S actually has derivatives of all orders, and the coefficients are related by this simple formula, which resembles a formula that for polynomials actually that you studied at high school. Okay, so these are, if you like, the Taylor. This is the Taylor formula of the coefficients. Okay, so in principle, you proved this theorem in the second year in a special course on series of functions. So I will not repeat it here, but we shall use this theorem. Okay, now definition. If omega is an open subset of C and f is a function defined on omega, we say that f is analytic at a certain point A in omega if f has a power series expansions around A. Okay, which means what? Which means that f can be represented by a convergent series, a power series about A. Okay, this is a definition, but this is a very strong condition on f actually, because not all functions satisfy this property of analyticity. And we shall now study some important properties of analytic functions that are not shared by other arbitrary functions. Okay, so, and we say that f is analytic on omega, on the domain, if it's analytic at every point of the domain. Okay, so we have now two concepts for a function of a complex variable. We have the concept of holomorphic, and we have the concept of analytic. And okay, so the first remark is that, so what is the relation between an analytic function and the holomorphic function? This is one of the themes of this course, is to prove that actually they are equivalent, generally. So the first thing that we remark by the theorem on differentiation term by term is that if a function is analytic, so it's locally the sum of a power series, but the theorem on differentiation term by term states that the sum of the series is holomorphic on a neighborhood of that point. So analytic at a point implies holomorphic on a neighborhood of that point. Okay, so this is the first remark. Second remark, so as I told you, we shall prove the converse. Okay, so We shall prove in chapter 2, but for this we need the theory of complex integrals. Okay. So we shall prove the converse. If a function is holomorphic on an open set, then it is analytic on that open set. So this is one of the main results of this course. Analytic and holomorphic are two equivalent notions. But there is a caveat. Pay attention. Because we have the notion of holomorphic at a point and holomorphic on an open set. And second thing, analytic at a point, analytic on an open set. Okay, so 4 different notions. Now, there is a difference because analytic at a point will prove that it's analytic on a neighborhood of that point because it's holomorphic on a neighborhood of that point. But a function may be holomorphic at only one point. Okay, this is the example that we gave last time. The function given by modulus square is holomorphic only at 0. So it's not holomorphic on a neighborhood of 0. Therefore, it's not analytic. Okay. So this is just, you have to pay attention on this distinction. Okay. And now I want you to pause the video and do this exercise for next time. Usually I let the students in the lectures, I let the students solve this on the blackboard, but don't have this occasion here. So I want you to solve this to show by going back to the definition that the function 1 over z defined on C star, so omega is C star here, is analytic on C star. Okay, now we know that 1 over z is holomorphic on C star because it's the inverse of a holomorphic function. But so we can conclude that it's holomorphic. So by the second remark, it's analytic, but we don't know this result yet. So I wanted to prove this directly by going back to the definition. So I want you to expand 1 over z in a power series about any point A, not 0. Okay, and this is not difficult actually, just use the geometric series. Okay, so but just to make sure that you understood this notion of analyticity. And by the way, in Arabic, analytic and holomorphic have the same translation. Okay, تحليلية, دالة تحليلية. Okay, now second definition, in order to study the properties of analytic functions, which are a very special class, as we know, we introduced the notion of germ of a function, of an analytic function at a point A. The germ of f at A is simply the set of all derivatives of all orders of f, because we know if it's analytic, it has derivatives of all orders. So the set of all derivatives, so we can consider f of A as f of 0, f of order 0. So the germ of A consists of all the derivatives at the point A. Okay, so this is the countable set. Now it's possible that this set is reduced to a point 0, for example. If this happens, which means that if all the derivatives, if f and all its derivatives vanish at the point A, then the germ is just simply the singleton 0. But instead of writing singleton 0, write just 0. So, okay, so this is what we call a trivial germ. Okay, so this is the notation. So the first result, so I will prove 3 results, 3 related results about analytic functions, which are actually generalizations of polynomials, okay, if you like, that you studied at school. So the first proposition is about the fact that zeros of an analytic function, if it's not trivially 0, are isolated. It's like polynomials. So, okay. So if we have an analytic function that vanishes on a point A inside its domain, but the germ is not trivial. The germ of f at A is not trivial, which means that there exists at least, so the first term here is 0, but among all these derivatives, there is some element which is not 0. Okay, so some derivative at A is not 0. Okay, so which means that f is not trivial, it's not 0. Then what is the conclusion? Then f doesn't vanish on the punctured disk, about A. So otherwise stated, A is an isolated zero. So in a neighborhood of A is the only zero. Okay. So all other possible zeros are at a certain distance from A. Okay. Why this is true? It's not difficult actually. We go back to the definition and work as if we work with polynomials, but instead of having a finite sum, have an infinite sum, which is convergent. Okay. So as I said, if the germ is not trivial, then some derivative does not vanish. Okay. So the set of integers k such that f of k is not zero is not empty. Okay. And so we take what? We take the smallest element of this set. We call it p. Okay. So of course it exists because every subset of the integers, of the natural integers, has the smallest element. Okay. So p is the first rank, if you like, at which the derivative does not vanish at A. So what does it mean? It means that before P, the derivatives are zero. And starting from P, so now starting from P, the other derivatives could be zero or not, but we know that Fp of A is not zero at least. But everything before is zero. Okay? Since F is analytic, we can write it, it's equal to its Taylor series, if you like. So this is just the definition, or it's a consequence of the first theorem, differentiation term by term. So I can write F, I can represent, if you like, F as the series, as a conversion power series near A. So, but the first P terms, so 0 up to P minus 1, all the coefficients of this series are 0. So actually the series starts from P. Okay. And therefore what? And therefore I have Z, so the series starts with something times Z minus A to the P plus something times Z minus A to the power P plus 1 and so on. Okay, so I have a common factor. I can factor by Z minus A to the P. So I put Z minus A to the P in factor, exactly as you would do with polynomials, but except that here we have an infinite series. Okay, so if I call this convergent series F1 of Z, then I have a factorization of F now. So F is a product of Z minus A to the P times another holomorphic or analytic functions. Okay, so we don't need now the fact that F1 is holomorphic, it just continues. Because what is F1 of 0, of A actually? If I put Z equal A here, all terms vanish except the first one, which is B0, because this is 1 when K equals 0. So F1 of A is just B0. Sorry, it's yeah, it's F1 of A, but it's the first factor here is F to the P of A divided by P factorial. Okay, which is equal to F1 of A. And so, but by assumption, F1 of A is different from 0. Okay, so if F1 of A is different from 0, continuity of F1 implies that F1 is still not 0 on a neighborhood, is also does not vanish on a neighborhood of A. It's just a consequence of continuity. Okay, so if F1 of A does not vanish, F1 does not vanish on a neighborhood that I call BAR of it. Okay, so what does this mean? It means that on BAR, A is the only 0, is the only root of F. Okay, there are no other roots inside the small disk. And this is the statement of the theorem. Second result, we establish equivalence between three conditions. The first condition states that there is a subset E of omega, if we have an analytic function f1 omega. So the first condition states that there is a subset E of omega having A as the limit point. So A is the limit point of E. and F vanishes on E. Now, in the exercises, we'll illustrate this. Okay, so F vanished, let us say, on, okay. The second condition states that the germ is trivial at A. The germ of F is trivial at A. And the third condition states that F is 0, vanishes on the whole neighborhood of A. These three conditions are equivalent. And once again, they are not true for a function which is not analytic. Okay, and can construct counterexamples actually. So we prove that 1 implies 2, 2 implies 3, and 3 implies 1. So we start with 1 implies. Now we don't know anything about the set E. It could be countable, it could be uncountable. Shall see examples. So it could just be a sequence actually, as we shall see in the exercises. If F vanishes on E and A is a point in the closure of E, then of course F vanishes at A by continuity. Okay, this is the first thing. So the first element of the germ is 0. Okay, now we reason by contradiction. Suppose that the germ is not trivial. Then I know that F does not vanish on the punctured disk of center A and radius R. So the disk, the open disk without its center. This is what I call the punctured disk. This is what the previous proposition states. Okay, so A is isolated, right? But by assumption, the number A is a limit point of the set E. What does it mean that A is the limit of this of E? It means that any neighborhood of A meets E at a point different from A. This is the definition, the topological definition of a limit point or accumulation point, if you like. So in particular, if I take the neighborhood, and I took BAR as a neighborhood, this set is not empty, okay? Because A is a limit point of E. So I choose a point Z0 in this intersection. So of course Z0 is different from A. Now, on the one hand, by the previous proposition, now we know that A is the only 0 inside BAR. So since Z0 is here in this punctured disk, F of Z0 does not vanish. This is because A is isolated. But on the other hand, since Z0 is in E and F vanishes on E, then F must vanish on Z0. And this is a contradiction. So what was wrong? This assumption was wrong. So actually the germ of F at A is trivial. Okay, so 1 implies 2. 2 implies 3. Since F is analytic, we can represent F in its Taylor series, right? On a neighborhood of Z. But if the germ of 0 is trivial, all the derivatives at A vanish at A. So which means that all the coefficients of this series are 0, near 0. So it means that F is vanishes on a neighborhood of A. Okay, so 2 implies 3. So note that, why do we call this germ? Because actually F is locally determined by its germ. If I know all the coefficients, I know F. Okay. So if you like, there is a correspondence between a function and a countable set of complex numbers. Okay. So now 3 implies 1. Okay. I need to show that there exists a set E inside omega having A as a limit point on which F vanishes. But this is okay, since now actually F vanishes locally, it vanishes on some disk, BAR, right? But now A is a limit point of this punctured disk, as you may check, because every neighborhood of A meets E at a point different from A. So A is a limit point of E, and F vanishes on E, and this is precisely what condition 1 states. So 3 implies 1, and therefore the 3 conditions are equivalent. And now we are ready to prove the main theorem of this lecture, which is called the principle of analytic continuation. Don't be afraid from the title. I will explain it now. It's uniqueness result, as I will explain now. Now, as usual, omega is an open subset of C, and now I have to put an extra assumption, which is the assumption of connectedness. So omega is one piece, if you like, and F is analytic on omega. If the germ of F at A is trivial, then F vanishes not only on a neighborhood of A, as this was the case of we know that from the previous proposition, but actually F vanishes on the whole domain, not only locally. So otherwise stated, because this condition means what? This condition means that F vanishes near A. So what we are saying here is that if F vanishes near A, it vanishes everywhere. Okay? And this is something very specific to analytic functions. It's not true, and I will give in a counterexample later. Okay? So this is a very special property of analytic functions. Okay, why? Proof. Consider the set Z in omega where the germ of F is 0, is trivial. Okay? Well, first of all, A belongs to S. Why? Because by assumption, the germ of F at A is 0. Okay, by assumption. So A belongs to S, and therefore S is not empty. First thing. Second thing, S is an open subset of omega. Why? How do we prove that? We will prove that S is a neighborhood of all its points. Okay, so take an arbitrary point Z0 in S. Okay, so that germ of F at Z0 is 0. And by the previous proposition, F vanishes on a neighborhood U, I call U of Z0. Okay, but if F vanishes on U, then all the derivatives of F vanish at U. So for any Z in U, the germ of F at Z is 0. Okay, and what does this mean? It means that S, so S is a neighborhood of Z0 because it contains a neighborhood U of Z0. Okay, so S is an open subset of omega. So S, otherwise stated, S is a neighborhood of Z0 because it contains a neighborhood of Z0. And the third observation is that actually S is closed in omega. Now, not necessarily in C, but at least in omega. How do I prove that a set is closed? One way is to prove that it's equal to its closure, but here I have to take the relative closure in omega, which is, we can prove is equal to the closure of S in C, which is bigger, intersected with omega. Okay? So I have to prove that S bar omega is contained in S, right? Because the other, the reverse inclusion is of course true. So I take a point in the closure and I prove that it's in the set. Okay, so take Z in the closure. Since Z is an S bar, there exists a sequence Zn of S converging to Z. Okay, this is the famous proposition 1.8 of topology. Okay. Now, suppose that by contradiction that Z is not an S, then every neighborhood of Z, since Z is the limit of Zn, meets the set E of all Zn's at a point different from Z. Okay, so Z is the limit point of this set, this countable set E. Now, since Zn is an S, and S is the set of points where the germ is 0, so in particular, the germ of F at Zn is 0. So in particular, F of Zn is 0. Okay, so F vanishes on E, on this countable set. And this set has the limit point Z. So by the previous proposition, the germ of F at Z is 0, or otherwise stated, F vanishes locally. This is condition 2 of the previous proposition. If the germ of F is at Z is 0, then in particular, so then by definition, Z is here, so Z is an S. So I took an element in the closure of S and I proved that it's an S. Okay? Actually, I got a contradiction here. So if I assume that Z is not an S, then Z is an S. So actually, what was wrong? So Z is not, it's not true that Z is not an S, so Z is an S. Okay. So what do I have now? I have S is now a non-empty subset, which is both open and closed. And now connectedness of omega implies what? Implies that S, because if omega is connected, the only clopen, not empty subset. So if omega is connected, what does it mean that omega is connected? It means that the only clopen subsets of omega are the empty set and omega. Since S is not empty, then necessarily S is equal to omega. If S is omega, it means that every point in omega, the germ of F at this point is 0. So F is 0 in particular. F of Z is 0. Okay? So this concludes the proof of the principle of analytic continuations. And now I have several remarks regarding this theorem. First remark, actually I already told it. What this theorem states is that if an analytic function vanishes on an open set, then it vanishes on the connected component containing that set. First thing. Now, why do we call this result the principle of analytic continuation? Because it's a uniqueness result. Okay, so let me explain this. Suppose that we have an analytic function on some open set omega. And suppose that there is a bigger subset, a bigger set omega prime containing omega, which is both open and connected. Okay, so if we suppose we have two extensions G and H of F, okay, so suppose that F can be extended or continued to two functions. One is called G, the other is called H. Then actually necessarily G equal H. So what does this mean? It means that an analytic function has at most one extension or one continuation. So it's a uniqueness result. Okay, so this is why we call it the principle of analytic continuation, because it reduces the number of continuations. Okay, it's at most one. Okay, because an analytic function could be extended but need not be extendable. Okay, but if it is extendable, then the extension is unique. Okay. And the third remark that we shall illustrate in the exercises is that if an analytic function vanishes on a set E, which has a limit point, then the function vanishes on the connected component containing that limit point. Okay, I will illustrate this in the exercise. Okay, so note that the set E could be anything. Okay, could be countable, could be uncountable, could be a punctured disk. Okay. Now, we already observed that, or I told you that the principle of analytic continuation is not true for an arbitrary function. Okay, for example, I'll give a counterexample. Consider this function, which is 0 f of t, which is 0 if t is less or equal than 0, and is given by the exponential of -1 to the t if t is positive. Now, of course, first you observe that t is continuous. Why? Because what is the limit of 1 over t as t tends to 0? This is minus infinity. E minus infinity is 0. So we observe the first observation is f is continuous, but it's much more actually. F is c infinity. How do you know that? Of course, it's c infinity at the negatives and c infinity at the positives. But it's a good exercise actually to prove that all the derivatives, f is differentiable at 0, has derivatives of all orders at 0, and they are all zeros. Okay. So here you can prove actually that f prime of 0 is 0, f double prime of 0 is 0, and so on. Okay, try to represent this function. I should have represented it actually. Okay. It has an S shape actually. So f is c infinity it vanishes on minus infinity 0, but it's not identically 0. Okay, so you have to pay attention in the real numbers between analytic function and function of class C infinity. So this is an example actually of a function of class C infinity which is not analytic. Why it's not analytic? Because if it were analytic, okay, all the germ of at 0 is 0 actually, but f is not identically 0. Okay. And last result, corollary of this, gives us some information about the set of zeros of an analytic function. So suppose that omega is an open and connected subset of C, and f is analytic on omega, but not identically 0, because if it's identically 0, the set of zeros is omega actually. Okay. Then the set of zeros of f is closed in omega, is discrete, has the discrete topology, and therefore it's countable. Okay. Now we recall the following fact from topology. If X is a topological space and A is a subset of X, actually you can take this as a definition. What does it mean for A to be discrete in the subspace topology? It means that every point of A is isolated, okay? Which means that A has no limit points inside itself, but it may possess limit points in A bar, okay? And I'll give an example later. Okay, so first of all, why the set of zeros is closed in omega? Simply because the set of zeros is the inverse image under f of the singleton zero, which is closed. Okay, but the inverse image under a continuous function is closed, so the set of zeros z of f is closed in omega, but not necessarily in C. Okay, it's closed in omega, so it's relatively closed. Now, suppose by contradiction that z of f is not discrete. Then, by definition, it would have a limit point that I call A in itself, right? So it means that there is a non-isolated point. Okay. But trivially, f vanishes on z of f by definition. So since z of f has a limit point, then by a previous proposition, f vanished, okay, actually by the principle of analytic continuation, because I'm assuming here that omega is connected. So f vanishes on the connected component of z, which is omega here. Okay. So, and this is a contradiction. So z of f is indeed a discrete subset of C. Now, why it's countable? Okay, this is a typical trick in analysis. Consider the set for each integer n, kn, to be the set of complex numbers which are in the closed disk of center 0 and radius n, and whose distance to the complement or to the boundary of omega is bigger than 1 over n. So what does this mean? So it means first that kn is a subset of omega, okay? Because z cannot be in omega c, because if z was in the complement of omega, this is the complement of omega, then the distance would be 0. Okay, so we are actually far from the boundary, but inside omega. Try to represent this by a picture. Okay, so imagine a domain omega and with a certain boundary, and we have an increasing sequence of compact sets that approximate omega from inside. Okay, so since the distance is a continuous function, okay, and the modulus is a continuous function, it's easy to see that Kn is a closed subset of C. But since it's bounded, it's compact. So Kn is a compact subset of omega of C actually, and we have yeah, I said this, and the union of all Kn covers omega. Okay, so we are approximating omega, if you like, from the inside. Now, if you consider the set of the intersection, if you consider the set of zeros of set of f inside Kn that belongs to Kn. Now, since z of f is discrete, the z of f intersected with Kn is also discrete. Okay, but z of f is closed in omega, therefore closed in Kn. Therefore, zf of this set is actually closed in Kn, which is compact. Now, closed in a compact is compact. So this set is actually both discrete and compact. So it has no limit point, right? Therefore, it's finite, because if it were infinite, it would possess a limit point, which is not true. Okay. Therefore, what? Therefore, now I can write z of f as the union of all these sets. Each one of these sets is finite, and this is a countable union over n. So the set z of f is countable because it's a countable union of finite sets. Okay. So this is the last result of this chapter. And just I want to illustrate a remark that I said before, is to illustrate the case where z of f may possess a limit point outside omega, but not very far from omega. It's actually z of f may possess, if it possesses a limit point, it's necessarily on the boundary. Okay, so for example, take omega equals c star. Then the boundary of omega is 0 actually, right? If you consider the function given by sine 1 over z, then f is analytic on c star because it's a composition of analytic functions. Actually, we can prove that, but okay. Actually, we can, of course, yeah, we can prove that directly, but you accept that f is analytic because it's holomorphic, actually. Now, where does f vanish? F vanishes when sine vanishes. Now, sine vanishes where? When 1 over z equal to n pi, right? So the set where f vanishes is the inverse. It's the set of all 1 over n pi, okay, for any relative integer n, not 0. Okay. So it's a countable set, of course. It's discrete, as you may check. It's closed in C star, but not closed in C. And it has a limit point, however, but the limit point is not in z of f. The limit point is 0. Okay. So it's in the boundary, actually, or in the complement of C star. Okay. So I want to just to pay to attract your attention to this fact when I. Okay. Now, I suggest now that you solve on your own 2 exercises. The first exercise, so we have omega an open and connected subset of C and 2 analytic functions on omega. We have to show that if the product of f and g is identically 0, then either f is identically 0 or g is identically 0. Now, this is not trivial because f and g are not just numbers. Okay, now this has a name actually in algebra. I think you call, so actually if you consider the set of analytic function, then it's a ring, okay? And this property that you want to show here means what? Means that the ring is integral. So I think you say it's an integral domain, okay? And I want you to also to show by a counterexample that if you don't assume analyticity, this is not true. So you can have the product of two functions may be 0 without having one of them being identically 0. Okay, so this result, okay, of course, this is a consequence of the principle of analytic continuation, but so it's not trivial. Okay, and the third exercise is typical. We always ask such questions in the exam. So the first question is find all holomorphic functions on the unit disk such that f of 1 over n and f of minus 1 over n equal 1 over n squared. Okay, and similar questions with different conditions. Okay. So Try to solve this on your own. I will give the correction next time. And I have to tell you that when the question is find all analytic functions satisfying something or find all holomorphic functions satisfying something, it means two things. Either there are no such functions, or there are very few such functions. Okay. And this concludes today's lecture and concludes chapter 1. Thank you for your attention and see you next week.